All right, everyone, so let's go and actually use this idea of a potential and figure out what's the atomistic origin of our thermal expansion coefficient. So we previously found that our Young's modulus is proportional to our curvature of our potential. So we've been assuming, again, so far that we are working at our basically we're very close to at our equilibrium distance. So we've derived this expression relative to those values. Usually it's this 1 over R naught, again, your equilibrium distance to R typically. But so we see this value here. So that was our atomic origin. How do we relate a potential to our stiffness? Now, my question now becomes, okay, well, how do we relate this potential, or how we could use this potential to figure out what's the origin of thermal expansion? Why do materials typically expand? And actually, you can see here, this is our Young's modulus, so it starts out high here, decreases. We'll explain that in just a second. But anyways, so let's go back to our old friend, our Leonard-Jones potential. So when our temperature increases, we're able to access and shake and basically vibrate more for our atoms, so they can oscillate around this equilibrium distance. So if the potential was symmetric or harmonic, basically like a quadratic function. So if our potential was like this, and this was our R naught, if it's perfectly quadratic, as I increase temperature, my material is basically, if I look at this, it's symmetric, right? So my atoms will, if I can access, at specific temperatures, as I go up in temperature, so this is T1, I can access all of these possible energy states. But basically being here or here, exactly the same. Same thing here. Like these values are exactly equal in terms of energy as the other values. But our Leonard-Jones potential is a little bit different. It's not harmonic, it's aharmonic. So if I look at my R naught value, if I am at a high enough temperature where I could access all these different oscillations, I see here that basically I'm not going to occupy a lot of these kind of regions right here. I want to occupy, basically at larger distances, you see the energy is not as high. So because they are asymmetric or harmonic, when atoms fluctuate, they're going to occupy positions with the lowest energy. So as temperature increases and the molecules move further and further apart, they're going to adopt lower energy positions. And on average, the molecules are going to expand because at the larger interatomic distances, there's lower energies, as you can see here, rather than being right over here. So it's a little bit hard to see in that figure because I didn't draw it as asymmetric as I would like it to be. But this is a good example. So if I'm looking at R naught, why would I want to occupy these high energy positions here? Basically if I'm oscillating, when I can occupy these low energy positions right around here. So I can occupy all of these low energy positions. If I vibrate more to this direction here, I'm going to be higher in energy, for example, than over here. So I can occupy these lower energy positions here. So you can kind of see again, your slope is increasing much more rapidly here in terms of the distance that we're kind of moving towards. So really, this is not really equivalent. It's like almost, if I can access the same amount of distance here, that delta, I'd be almost way up here on this curve. So it's a little bit kind of hard to, to visualize, but you can kind of see where I'm getting in that picture. So most atoms are going to want to adopt this kind of larger state. So, you can kind of imagine like exaggerated here. Look at this distance, right? So if I were to draw an equivalent size here, I'd be way up on this curve. So I definitely don't want to be there. I want to be in these lower energy states right here. So my materials want to adopt lower energy conformations. So instead of getting closer together, they are going to tend to expand, except for some exotic materials. So we're going to be at our equilibrium distance, and then they're going to shift that equilibrium distance, or the atoms, the distance they're going to occupy is going to shift to the right, and then your material is going to strain according to this very, very important. And this is going to add on to our kind of strain values in a little bit. So for linear elastic isotropic materials, the expansion is going to be uniform in all direction. That might not be the case for certain problems, certain anisotropic materials, and you can kind of see some typical values that you see here. So polymers are going to tend to expand again. So it's again expansion per K. So because again alpha times delta T strain. So if you look at this, this is going to be inverse K. So millimeter per millimeter inverse K. So that's essentially the units that you're going to be working with. So that is essentially that in a nutshell. So think about that the next time that you're working with this. So thermal strength is very, very important, especially when you have, we're going to have some problems where if you basically, you can have some stresses that can, residual stresses that form due to incompatible thermal strains. So as that material cools down or expands, and actually there's a couple of cool examples we could do. If you've ever done boiling an egg and then you just put the pot immediately in cold water and you still have the top on, you'll find that that material is just stuck. And there's a cool little problem that we may do on either on a problem set or an exam. I haven't decided which yet, but be ready for that. Now, additionally, you could also start to kind of think, well, if this is the case, how is, and I know that my potential is related to my curvature, how is my Young's modulus going to change as my material heats up? So you may think of basically a problem related to that somewhat. So we'll consider that just a little bit later on. So you can see your Young's modulus slightly decreasing here. I wonder why. Maybe there's a problem that we could do with that. So yeah, we'll see that just a little bit later. All right, excellent. So now we are going to move on to a very, very fun topic, at least to me, and that is rubber elasticity. So what is the atomistic origin of the elasticity of polymers and rubbers? So we'll get into that in several videos next time. Thanks. See you next time.